Welcome again to the NPTEL course on storage systems. In the previous class, we were looking at some aspects of file system design, and we will continue from where we left off last time. So, I think we were discussing something at this point, and we were talking about how it is critical that you need to replicate critical structures or find some mechanism by which you can recover in case there are hardware problems. And if you look at some of the more recent file systems, for example, ZFS from Sun is a good example of this. They discovered by talking to various customers that avoiding corruption of the file system metadata or data is quite critical, and there is some already data saying, for example, that in large scale systems almost every 15 minutes or so there is a silent corruption, every 15 minutes. If we're talking about very large web hosting kind of places or cloud kind of computing places, every 15 minutes there is an error, undetectable error. Of course, you can detect it through checksums. What I mean by saying undetectable is that you are using disks which have Reed-Solomon error codes. They do a lot of extensive error control, but in spite of all that Reed-Solomon codes, there are still errors that are undetectable unless you handle it through some mechanism checksumming at file system level. Okay. So, ZFS, for example, tries to do some of these things, all these aspects. Okay. So, traditional thing is best effort service, as we were discussing last time. If there are any soft errors, that means if you retry it one more time, the error goes away. You retry it a few times. If it does not go away, then you declare loss. Okay. And this is typical of SCSI. And hard errors are things like, for example, which cannot be recovered. Is you get an indication that disk is dead. Okay, things of that kind. Okay. So, as we discussed last time, in case there is error, in spite of all the checks you have put in, you somehow have to still salvage the situation. You can't just walk away. You have to find some way of getting the file system to some reasonable state. Okay. It has to be a consistent state. You might lose some data, you might lose something, but it has to be still some kind of a semi-reasonable state, so that forward progress is possible. Okay. And nowadays there are some newer standards that are coming. There is something called data integrity format, DIF, wherein they try to do end-to-end checksums. Okay. Now, you will notice that in a piece of data, when it is transiting from the CPU to memory to network to disk and back and forth, and there are various buffers all over the place. Okay. There is a buffer sitting in the disk itself, there is a buffer in the HBA, there is some buffer in memory, of course, and so any one of these things can get corrupted, okay, in principle. And usually you have ECC memory, error correcting code memory, but even that can only handle 2 faults. It cannot handle more than 2 faults. Okay. You can detect if there are 2 faults. If there is one error, you can correct it, but more than that, it is going to be serious problem. Okay. So, you have to find a way in which, in spite of all these possible error locations, you still can discover whether you are doing something right or wrong. Okay. So, a diff disk basically is one attempt at doing what is called end-to-end checksums. Okay. And this unfortunately requires some major changes, basically because if you are talking about end-to-end checksums, you need to attach information about the checksum somewhere. So, every block, for example, let us say it is 512 bytes, you need to attach some information about this checksum. So, it cannot be a 512 byte sectored disk, it has to be 520 or whatever, 524, whatever. Okay. That means that your on disk format has to change. Okay. That means your support for sectoring as required by the needs of this checksumming has to be possible. Okay. If it's not possible, you can't do it. Okay. And in addition, there are even more interesting complications here. For example, when you are writing to disk, it may be that usually there is a servo motor which takes you to the particular track. It's possible that once in a while, instead of going to track number 100, it might go to track number 101. So when you write it, it is actually returned 101, not 100. So if you just do the checksumming on the data, that will work out quite okay, because finally that's a block, you have data, you wrote it, and there is a checksum corresponding to that, and it depends only on the data. So checksum is still okay. So even if you write on 101 track, if you just only checksum the data, you can't figure out that something bad has happened. What do you need to do? You need to not only checksum the data, but you also have to checksum along with it some information about which track you are trying to write. You also have to incorporate into checksum the fact that you are trying to write track number 100 or sector number so and so. If you do that, then when you try to read it next time, you ask for 100, and then, you went to look at the track number 101 sector something, you pick it up, and then you again do the same checksum using information from the data plus the sector number / track number that you were thinking about, then it won't match. Then you know something bad has happened. Somebody has wrote into the track number 101, and it actually clobbered some previous information. Okay. So you need some additional piece of information also, and these are of course very specific to the devices. When you talk about disk, we can talk about track numbers. When talking about other kinds of devices, there might be some other things. Okay. So that means that this end-to-end checksum is going to be highly device specific and technology specific. Okay. So, and of course in the case of networks, people have known all these kind of problems. In networks, typically it turns out that for example, there are some studies which have shown that if you are using ATM, for example, there is something called asynchronous transfer mode, ATM, which used to be quite popular some time back. It is still used in the backbone of the internet in a few places. It turned out that there are some bugs where each of these 8-bit quantities can get flipped. Okay. There are some unusual situations where if you have a 16-byte quantity, the two 8-bit things get flipped. Okay. And this has been shown to result in network packet errors as high as 1% or 2%. Of course, this I am talking about some old information, I am talking about 2001, 2002. Okay. So this end-to-end checksum is highly, I just wanted to mention that it is highly technology specific, and you have to, because you essentially are trying to work around the kind of problems that the hardware is throwing up. So by definition, it has to be technology specific. Okay. Now, one of the things I mentioned that these systems, they usually give only best effort service. There are no non-starvation guarantees. The reason why they can't do it is because the hardware itself is not giving any guarantees. Hardware can do arbitrary things. Okay. So if you are trying to work around it, okay, often you don't have a way of working around it. Okay. For example, if you are doing soft errors, retry, okay, there are usually some timeouts involved, and the timeouts are set by your expectation of typical situations. If it happens very rarely, your timeout is going to be large. If it happens quite frequently, you may want to keep it slightly smaller. Okay. So, reason why you want to, I think it's quite obvious. If you want to, if it's very unlikely, right, you want to wait for some time thinking that it will correct itself somehow. Okay. If it is reasonably often, then it is, since it's often, then probably something actually has gone bad. You might have to do something about it. So the timeout basically is a highly, again, dependent on the context in which you're using the system. Okay. So because of this, if you're planning to build a real-time system or any of those things, or you want to give some bandwidth guarantees and whatnot, it turns out to be slightly difficult because of all these assumptions all over the place. Okay. You really can't really provide very strong guarantees. And it also turns out that these non-starvation guarantees are not possible because of the way some events in the system interact. Okay. I think we will just take one example of that. This is an example of a lookup. Okay. You are doing a directory, somebody is doing a lookup on a file, okay, and there can be some serious delays involved. Let us see what that is. Okay. So, what is happening? There is some, suppose you have a file on which some slow operation is taking place, very slow operation, because that means that it is somebody has done a what is called file locking. This file locking is available at user level, okay, and the user is updating things very, very slowly, let us say. Okay. For example, it could be that you are picking up data from through a network, and the network is sending you bits very slowly. That means, as a user has locked a portion of the file, and this will not be dropped till the operation completes. Okay. So, in a sense, you can have some, you can imagine some slow operation. Okay. Now, by bad luck, if you are trying to, somebody else is also looking up that file, let us say we are coming to NFS. Okay. Now, when you are trying to look up some information, you want to make sure that the information looking for is stable. The way you make it stable is by taking a lock on the directory, okay, the parent directory, because that basically says that nothing can change corresponding to that file, because the metadata of that particular file is going to be kept in the parent directory, right. For example, its size and all those things. Okay. So, you basically, if you will take a lock on the file, okay, basically what you do is you take a lock on its directory, then you are basically guaranteeing that whatever changes that are possible on the file is not possible, okay, until you get the chance to get the lock. Okay. So, now the basic problem is that the directory is now locked. Okay. Nobody else can, if somebody else innocently does a lookup on that directory, for example, somebody could be just searching for a particular file in the directory. Okay. They want to see if that particular file exists in the directory. So, to again make it stable, you are going to take a lock on the directory. Again, to do that, you have to take a lock on its parent. Now, this can keep on going all the way up. That means that your operation can be arbitrarily slow depending on when the user has released that file locking. Okay. There are no guarantees now. Okay. So, that is why it is extremely difficult to, because the way these things interleave, the events in the system, they are extremely difficult to predict, and if it happens in a way which is unexpected, there can be arbitrary delays. Okay. So, that is why usually these kind of systems never give you non-starvation guarantees. If you really want to worry about these things, if you really are interested in building a real time system, etc., then you somehow make sure that these things are in memory if possible. Even in memory, the same problem can be there. Okay. There is no escape here also. Okay. So, because if you build a, let us say, a memory based file system, the identical situation also can happen. Okay. There is nothing which says that it cannot happen, except that the time involved, amount of time involved probably is smaller. Here we are talking about disk speeds, so you can actually be hit by it seriously. Okay. Okay. So, this is, I just wanted to mention that usually most file systems never may give you these non-starvation guarantees, okay, because it is difficult to provide. And in the case of again connecting to the same aspect like real time guarantees, etc., there is a issue of quality of service, and usually these things are usually also not seriously provided, basically because you need to really take control of bandwidth and latency issues, which are somewhat difficult to manage currently. Okay. For example, one way to minimize, to provide high bandwidth in the case of mechanical components, electromechanical components like disks, is to minimize the number of seeks and rotational delays, okay, or you aggregate requests for contiguity, okay, you have to do some of these things. Extensive amount of aggregation, clustering, all those kind of things have to be done, okay. This is the only ways to ensure that your bandwidth doesn't decrease, okay, because the minute you start having seeks and rotational delays, you are talking about some multiples milliseconds, that itself will kill your bandwidth. Okay. And in the case of latency, you have to do some scheduling. We have already looked at some aspects of this, and you also have to manage parallelism across devices. Okay. So, now the issue for us is when you are trying to manage parallelism across devices, we also have to somehow understand that there are issues of failures also. Now, we have to interleave ability to flush certain data to devices, we want to do it parallelly, but in the context of failures. So, if failures occur, again we have in a slightly tricky situation. Okay. That is the reason why some of these things are usually not really done at the file system level. It is expected to be done at higher levels, where the user knows what to do when some bad thing happens. The file system not being given information about what to do when multiple parallel activities are sent out and then certain failures occur. It has no idea about what is important, what is unimportant. Okay. So, this is best handled at user level in case user knows about how to handle it. Okay. Again, this is usually not something that is done at the file system level. Okay. So, we will just look at some high level designs. What are the types of designs that are there? One thing about a file system is that it attempts to, in any update of its structures, usually it touches multiple pieces of data. For example, there is metadata and data. So, when you update a file, you not only update the contents, you also update its access time, the file size, etc. That means that you have to update both metadata as well as data. So, since it is not possible to update multiple disk blocks atomically, and no hardware does not provide you that information, okay, does not give you that capability. That means that you have to figure out a way of forcing these changes in a particular order, okay, in spite of whatever the devices are doing. So, one of the first earliest models is what is called the ordered writes. You figure it out that this has to be, something has to happen in a particular order, and you do synchronous writes one after another. Synchronous writes, the thing you do it is you send the write to the disk and wait for it to be completed before you proceed. Now, that is very slow, extremely slow. So, you need to find some other ways of doing it, and there are many methods of doing it, and this basically these methods, journaling, etc. Okay. So, if you are not bothered about correctness that much, or you are willing to take the risk, ordered write is still a good model. Okay. So, that is the reason why the previous file systems in the past, up till about 1990s for example, most of them are based on ordered writes. They were never really, they just said that in case something bad happens, power failure, whatever, you have to figure out what to do with it, whatever has happened. Okay. And typically it used to be the case that in those days, personal computers were still not that very common, right. So, usually any machine, Unix like machine was managed by a system administrator. So, if some crash took place, somebody was, a reasonably competent person was there to take care of it. Nowadays, with large scale computing systems available to end users, it is not a good idea to assume that user knows what to do in case there is a crash. Okay. So, now these kind of models have become more appropriate and reasonable. Okay. It's always good to make it as surprise free as possible, the file systems. Okay. If something bad has happened, you let the file system figure it out, how to fix it. Okay. So, the kinds of things that people attempted are things like journaling file systems and other models. We'll go through each one of this a bit. So, in journaling file systems, what happens is that you do logging, and then you first make sure that all the changes are in intent log, and from there it goes to the what is called home locations. Okay. Whatever changes you make, first go to the log, and then once the transaction is completed, you trickle back from the logged values, it goes back to its home locations. For example, if you are writing a file A, the data corresponding could be of the write of the file could be written to the log. It won't directly go to the file. Okay. And then once the transaction is completed, once is successfully completed, there was no power failure, any of those things, then you can think of writing that data from the log to the file. And you read the log only in case there is a failure. Okay. Sorry, I made a mistake. If you are doing logging, once you are going to trickle back the information from the log to the file, okay, and that is the normal thing. And then if there is a failure, then you go back and read from the beginning and see what has happened. Okay. That's what I meant to say. So, the problem with generating file system is that you now have to write two disk places. One is the log, and then from there to the home location. So it is going to be slow. Okay. The good thing about this is that you write into the log whatever changes are going to take place, so that you want to roll back, it's easier to roll back. Okay. Now, typically in file systems you use what is called redo only logs, because the transactions are typically small. They are small duration. Whereas in database kind of situations, the transactions can be long, so they usually have redo undo logs. Okay. So basically, in some sense, in file systems, they assume that you can always move it forward. Okay. You can always take some changes in the forward direction, and whereas in database sometimes there could be incompatible transactions you have to roll back. Okay. Okay, so this is one type and it is quite commonly used. Now, in this generating file system kind of models, you might log only metadata, or you can log data. There are various possibilities here also. So, there are some file systems which only log metadata, because logging data is going to be expensive. Okay. So, or file systems allow you all the possibilities, but you have mount options. In the mount options, you tell exactly how you want to log it, whether you want to log the data as well as metadata or only metadata. If you log only metadata, then there could be a problem there also, because you might have dependencies between data and metadata that have to be captured. And then if you only log the metadata, then some of the dependencies with respect to data they could be still sitting only in memory. There is a power crash when there is a loss of power, then you only have information about the metadata, but no information about the data. So that also can get into some trouble. But these are the kind of things that people have done in the context of widely used file system. For example, ext3 has some of these models. Okay. You can do metadata only logging, you can do metadata plus data logging. It's up to you. You decide for your application what kind of guarantees you want, and you decide it. Okay. There is also another model called soft updates, which is there in the BSD file systems. I mentioned previously that when you do a lot of clustering, you can get into some trouble, and soft updates is one way in which what you do is any things that have to be flushed to disk, first you have all those modifications in memory, and then you basically try to flush the changes from memory to disk in a particular order, similar to ordered writes, but keeping in mind that you are doing clustering. Let us see how clustering, I briefly mentioned last time that clustering can introduce certain dependencies which should not be there. This is an example of the kind of problems that occur with if you are trying to keep track of dependencies in memory and you want to flush them in a particular order to disk. Suppose you have the following order in which you have to flush things, that is, let us say A is the inode and small a is inode and capital A is the data, let us say. And similarly, capital B is the data and small b is the inode. I am just taking a random graph here, please do not read meaning into this thing, but this is possible, all these things are possible. Okay. So, what it means is that this inode A should be flushed first, followed by the data corresponding to A, and then let us say for some reason A has to be flushed first, followed by B, and then for some reason data of B should be flushed first, followed by its inode. Okay. Let us say that some such thing is there. As I told you, it is totally fictitious, but this kind of real dependence can be easily possible. Okay. Now, so in a soft update, you basically all this is sitting in memory and you are trying to flush them to disk in a particular order. Okay. That means your buffers are there, there are some headers in the buffers, you keep track of these dependencies. Anytime the flush daemon comes in, that guy looks at each of these things, it goes through all the dependencies and does it in a particular order. It looks fairly straightforward. But let us see if I am trying to do, in addition to this flushing, suppose I am trying to also do for efficiency of the disk, I need to do what is called clustering. What is clustering? I notice that A and B are only, let us say 128 bytes and this is 128 bytes, whereas this is 4 kilobytes and let us say this is 4 kilobytes. And I tell myself, why should I do just a flush of A? Because what is the problem with just flushing A, small a? Basically it becomes a read modify write cycle, because I am only updating 128 bytes. So that means I have to read, and let us say I am only accessing the block device at 4 kilobyte chunks, let us say. Then in that case, I want to update 128 bytes, I have to read in the full 4 kilobytes corresponding to the block where A is residing, get a full 128 byte, then update it in memory exactly at 4K what I have read in, update that small portion corresponding to that small a, then write back the whole thing. So it becomes what is called a read modify write cycle. Okay. So that itself is costly. Now, if you want to avoid those kind of situations, the right thing to do is clustering. See if I can put as many inodes as possible which can fit into 4 kilobytes and flush all that inodes in one shot. I will not mix it with the data because data usually is in 4 kilobytes. Of course, I can mix inodes and data also if in case you want to do it, but let us for simplicity assume only inodes are clustered together and data is clustered together, let us say simplicity. Okay. Now, our problem is that if I, let us say in some clustering scenario, if I get A and B to be clustered together, now what will happen? It is basically saying that this particular graph now is circular. It is basically saying this has to be flushed before A, this A has to be flushed before B, B has to be flushed before this combined thing. This circular, okay. Basically the graph is now a cycle, okay. Now that means that once you start doing clustering, you have started introducing additional dependencies, spurious dependencies, which did not exist before, okay. So the software basically takes care of how to handle these things, and the way you do it is again something similar to what people do in the case of transactional models, where you have to unroll some things. You cluster some things, and then as you are flushing them, you discover at runtime you figure out that having flushed so much, if I were to flush this particular thing, I might actually create a cycle. I have to unroll some things so that I still have acyclic graphs, okay. And then I do it in that way, okay. So basically you cluster them tentatively, but unroll some of them in case you find that creates some kind of cycles, okay. So the soft updates also is it's a good model, and the only thing is that there is some complexity involved in figuring out these cycles. So basically you have to keep on running strongly connected components and all this kind of algorithms all the time, okay. So that can be expensive, but probably is less expensive than the kinds of delays that are there with respect to disks if you do it in synchronously. So again there is some kind of trade off, whether if I do synchronous writes, is it more costly than doing all this computation at runtime as I am flushing it, okay. The BSD file systems use soft updates, okay. Okay. There is also other issues about whether you update in place or not. There are multiple designs here. I can have what is called a log structure file system, for example, where I write everything to a log, and the log is actually my file system. There is nothing other than the log. So if I want to see the most recent version of some particular block, I have to scan it backwards. If I want to read, for example, right? I am just keeping on making modifications to blocks, and in some sense there is some kind of versioning going on. If I want to get the most recent version, I have to scan from the most recent end of the log and then go backwards and find the first copy of it, okay. So writes are simple because I am always writing at the end. Reads are complex because I have to scan it backwards, okay. So And the issue about this kind of file systems is that once you are overwriting a block, the previous blocks become garbage, because they have to be garbage collected. Question is, when should I garbage collect? Okay, that becomes an issue here. Okay. So you have to, again, once you garbage collect, then what will happen is that there will be in that log, for example, there will be holes now. So do you compact it? If you want to compact it, you have to copy things, right? So all these issues become slightly big issues. So the standard thing to do it is to do all the writes onto a buffers, okay? So have so many segments, what are called segments, and then keep it around for some time, and then you keep cleaning them with respect to dead blocks, for example, and then once you find that they are reasonably complete, then you flush it to disk. Okay, so that's something typically is done. Okay, so log structured file systems have been quite. It's a very nice idea, and it has found its way in many different ways. I think, for example, when we discuss the Google file system, they also have some kind of a log structured file system there. If you are talking about things like flash based devices, they also find that having some kind of log structured file system is useful to get all the writes in one place and then later do updates as necessary. Okay. So this log structured file system is a good idea and has been used in different ways in different places. Okay. So basically, in some sense here what you are doing is you are not updating in place, you are always writing it to some new locations. And this also has been used in some other context. You do not update in place. What you can do is, anytime you are writing, right, what you do is you do not seek to the place where the data is, you write to some nearby place, wherever the disk head is, let us say, and then flip the pointer to point to the fact that logically it should be pointing to this new place where I wrote it rather than to the place where it originally existed. Okay. So what you can essentially do is, you have a disk arm which is moving. If you are able to find a way in which wherever you are, there are a few blocks always available, let us say that is always available. Suppose you make sure that the system is structured in such a way that wherever you are, there are some free blocks available. That means when a write comes in, you look for the closest free block that is available, not to the original home location, not where actually the data resides, because you are not going to do update in place. You just basically look at the nearby place where there is a free block available, right there, and switch the pointer. Originally it was pointing to the home location wherever it had the actual data, which you would have gone to if you wanted to do a read, right. Now instead of going to that place, you just flip the pointer, saying that the newer contents are pointing to the place where I am just right now. Of course, this creates some problems like fragmentation. That is, if I want to read something, some part of it is here, some part of it is there, some part of it is here. Okay, it's not exactly in sequence. That means again your read performance really goes bad, but your write performance is good because you are never really seeking to when you are trying to write. So various things have been attempted like this. Okay, so the good thing about update in place is that it can be married to a transactional model also. Okay, because in transactional models, what is the issue? The issue is that you want to either be the old or the new, right. Now the thing is, if I keep all my modifications, right, so that it does not go to the home locations, nothing is updated in place, then basically what it means is that you can play with your pointers so that you have an old copy and the new copy, okay, and then you can just switch. You can go from the old to new in one shot. Basically, I have a tree of pointers, and then if I want to go to the new thing, I just switch the tree of pointers to the new one. Okay, that can be done atomically because it's a memory operation, or it can be, if you want to make it to disk, you can flush all those things to disk one by one, the updates, but the very last one, which actually does a switch, that's a single block now. Okay, you send it, that can be done atomically. Okay, at a sector level, for example, and typically most disks give you some guarantees about writing a single sector. Okay, there is some capacity in the system, whatever, it can write that particular sector, okay, atomically. So this non-updating place can be easily married to a transactional kind of system quite well, and you will see that, for example, many commercial systems do this. For example, there is something called in NetApp, there is something called WAFL, WAFL, write anywhere file system. Okay, this particular system uses these two ideas. Okay, it's transactional, write anywhere. Okay, and another example is ZFS, which also does something similar. Okay, so one other thing I just want to mention is that there are a lot of dimensions to the design of the file systems, but I just wanted to mention a few other dimensions. So far we looked at all this stuff is connected with how to do atomic updates. Okay, but there are other aspects of the design also, whether you are disk optimized. For example, do you think that disks are what is holding a file system or something else? Suppose I am disk optimized, for example. Suppose I assume that I can only live with disks. Then my problem is the following. Okay, I have data and disk, metadata, right? Usually metadata and data can be in different places. Okay, that means that when I am writing a file, I have to go to the metadata as well as data. That means by definition I am forced to go, I have to make a seek. I am forced to make a seek because first, suppose I want to make the file write committed, okay, because there is something critical for me. That means I have to do not only go and finish the flush of the metadata, but also do a seek and get to the data also. Now, if this is slightly intolerable, because you are essentially talking about a seek to metadata, flush to disk, again seek to data, flush, right? That means you are talking about minimum 2 or so of seeks or rotational delays plus 2 disk writes. Okay, and this can come close to about anywhere in the current disks, it can be about 50 milliseconds. So at the most you can do 20 writes per second. Suppose this kind of speed is extremely low. Okay, you can't handle this, right? You want to do something else. Again, if it's only disk, for example, you have with you, what you can do is there a way in which I can separate metadata and data? And this is oftentimes called multi-device support. That is, what I do is I have 2 sets of disks. One of them holds only metadata, another holds only data. That means that I can now keep on writing. For example, if my data, it is, let us say, a large quantity, okay, let us say it's some megabyte, then I can keep on continuing writing onto the disk without being disturbed by other concurrent activities in the system which are also doing metadata writes. The metadata writes are going on the other side. Okay, so I can essentially have some ways in which I can partition the system so that the metadata is in one place and they are getting access somehow sequentially somehow, and data also is getting access sequentially, and therefore I can try to do better than the previous situation where data and metadata were together in one place. And these kind of things are also can be attempted in the case of those systems, file systems which are based on things like flash and other kinds of devices, because even in flash, for example, it turns out that some people say that flash writes are faster, let us say, small flash writes, because you do not have the component of seek and rotational delay. So even if disk bandwidth is about the same as flash bandwidth right now, the fact that you do not have few milliseconds of seek or rotational delay can make your writes faster. Okay, so you might want to, if you are metadata intensive, for example, you may want to put the metadata in a flash based device. Okay, so various kinds of permutations are possible. Okay, it's up to you to decide, depending on your context and your requirements. You can partition your data structures in your file systems differently depending on the characteristics of the device. So all those design optimizations are possible. There is also a question of whether you want to be based on your file system design is it based on set of pointers to various disk blocks like a typical file system. For example, the inode essentially keeps track of various blocks and these are pointers to various blocks, right. Do you want to do it like that, or do you want to have an explicit B tree kind of model, so that you can somehow bound the amount of the height of the tree, okay. If you are able to do that, it will be helpful. This is especially true for multimedia file systems. In multimedia file systems, typically what happens is that you are talking about large files, and regular traditional file systems, you have what is called direct blocks, which access about the first 40 kilobytes or so directly from the inode, okay, because there are pointers to blocks directly. But once you go after 40 kilobytes or so, you have to go through indirect blocks and also what is called triply indirect blocks also. That means you have to go through another levels of disk based indirects, okay, which if you are doing a multimedia kind of file system where timeliness is important because you are talking about video playback and other things, these indirects also can create some jitter in the system. It can essentially suddenly certain frames cannot be displayed fast enough, okay. So, in those kind of systems, your design becomes simpler if your file, for example, irrespective of the position, it has got the same kind of latency behavior, okay. So, in the case of regular file systems, your first 10 blocks got easy service, they were able to be serviced very quickly, but later ones always suffered through indirects. Whereas in B tree, everybody gets the same treatment, okay. So, again, it turns out newer systems are typically also B tree based. Most of the new ones, big ones, they usually are B tree based. The other aspects of design also, I said there are many dimensions, I just wanted to list a few. You can also support what are called triggers. Oftentimes what happens is that you want to know when a particular file has changed, you want to be notified, okay. And for example, you might have a compressed file system and then you try to read it. So, this compressed stuff is on the disk, and the minute you try to read it, I want to provide that information to a process, and the process wants to look at only the uncompressed part. It does not see it, for it, it's not going to. So, let us say the process is not interested in doing it does not want to do decompression. Okay. It wants to have a transparent way of looking at data. So, the minute you touch it, you want to interpose a process which will actually decompress it on the fly and provide that information to the process. Okay. So, this requires some kind of triggers, that is the minute it is accessed, you need to be given a callback, the kernel notices that something special has to be done, it will in turn will give an up call to a process which is a decompression routine or decryption routine for example, which will in turn make sure that the data that is going to be given by the file system, actually it is read from the disk, but it is again massaged appropriately. Finally, it is decompressed and then made it look like a regular block of memory, and then this is what the file system actually returns back to the process. So, neither the file system nor the process knows that somebody has come and done some decompression or decryption and done it. So, slightly delicate design, but there are ways in which this can be done. Now, there is something called data management API by which this kind of stuff is done. Okay. What is critical about this is that both the file system and the process do not know that decompression or de-encryption has taken place, and none of them they know it. Okay. So, while actually lot of things happen in between. Okay. Otherwise, then it becomes non-transparent. Okay. So, you will find that for example, some of the more advanced file systems provide it. In Linux, for example, XFS provides this capability. Okay. Not every file system provides it because it's slightly difficult to provide. Okay. Because it interacts with multiple things. It interacts with the virtual memory subsystem. It interacts with, of course, the file system. It interacts with the kernel abilities to do upcalls to various random procedures, all kinds of things. There's a lot of things that have to be provided so that you can support it. But this ability to support triggers is extremely useful, and it is used extensively in many. I'll just give you 2 examples, but it can be used in lots of situations. Okay. It can even be used, for example, somebody reads something, you want, there's some error that has taken place, I want to call an error routine to fix the thing, all kinds of things that are possible. Okay. Okay, now the typically it turns out these file systems are fairly complex beasts, because as I told you, it interests lots of things. So, the way they reduce the amount of complexity is by using abstractions systematically. Okay. So that it becomes slightly more easy to manage. So, the abstractions are typically like, for example, buffer related, inode related, various other things, kernel related, etc. Various kinds of abstractions are used. Okay. So that these abstractions make the writing of the file system slightly simpler. Of course, these are all kernel based abstractions. That means that these are all not, let us say, these are not available at user level, okay, but these are used inside the kernel, and there. For example, in the case of buffer related, there are various types of calls. For example, get block, right. So, given a file system and a disk block, you want to get a unique buffer, but it is also locked. Okay. So, if anybody else asks for the same file system number, block number, it still should get the what was given earlier out. Okay. There should not be two copies of the same thing, because otherwise then each of the parties can write to it and they will be inconsistent. Okay. So there is a routine called get block, and of course this depends on various versions of file systems. If it is highly concurrent, multi-threaded kernels, there will be all kinds of differences here. But in general, there is some function called get block, okay, by which what you are guaranteeing is that if there is a block in the disk, there will be only one copy of it in the file system, in the memory, only one copy of it, across all users, across all threads, okay, there is only one copy of it. So, if any modifications take place, it goes to only one place, okay, that is the basic guarantee that they want to give, okay. So, that is what get block does. You can also have B release. You can, for example, once a write has been done, you want to release the buffer, okay. And of course, if it is dirty, it has to be flushed to disk, but the idea is that you release it. If somebody wants to reuse it, then they will notice that it is dirty. It is their business to flush it before they can reuse it again. And if it is left dirty for some time, if somebody wants to look at it, they can still look at it, because it is cached in some sense, okay. That buffering basically is giving you that caching capability. At the same time, if you get a log buffer, it might be possible that while you are writing it, other people are waiting for that, right. There is, you got something from somewhere, you updated it, but while that was going on, other people also wanted the same thing. So, they all will be waiting for it. So, as a part of its job, the B release actually wakes up any process that is waiting for it also, okay, and unlocks it, okay. So, this is a typical kind of usage, that is there. I would say that if you are looking at any file system that is derived somehow from the old Unix Bell Labs file systems, we are talking about file systems that were there from 1980s. They were using these things, and you will find similar things. Even current generation file systems are Unix based. If you go to Windows based file systems, you may not find similar exact abstractions, but it is there. For example, Linux actually uses some of these things. There are similar functions. They differ in details, but mostly it is you have similar functions. Okay. Again, if you want to read a disk block, okay, you can use bread. You can also bread A. Basically, you do a bread of one block, and then you do a asynchronous read of the next block, okay, next logical block. Of course, this actually you should notice may be wrong, because what it is going to read next is the logical block, and it usually should be actually again mapped again to see where exactly the physically it is located, but that is too costly to do it. What they do is they just read the next physical block, with the assumption that typically things are, there is some correspondence between logical and physical let us say layout, and therefore, the asynchronous reader head actually goes and reads the next physical block, not the next logical block, okay. in principle it should be next logical byte, but it's not what it's not. Okay. So again, write a given buffer to disk block, basically allocates a free disk block and return buffer using get block. Okay. Basically, you have to allocate a free disk block here, then only you can do a get block on it. Okay. So this is a higher level routine which uses get block. And of course, if you look at allocate a free disk block, what you are doing is you are updating your information about which blocks are free, right? And the question for us is, do you keep this information also persistent, or do you keep it in memory? Okay. Now, if it is a generating file system, what you do is, when you allocate a free disk block, you have to flush the intent that you are actually going to make this non-free. You are going to essentially allocate the disk block, that particular thing has to go to disk. So what you do is, again, if you are going to do it that way, then for every allocation you have to flush to disk, which is again costly. So basically, you keep on writing to memory, you keep on having a log in memory, which is keep on added to it. You don't flush it, but flush it at some point in future. Now, in case some bad thing happens, you lose all these things, but everything is still everything is consistent. You have lost lots of things, but nothing has ever made to disk. And if you assume that whatever you are writing to disk is always consistent, suppose you always guarantee that, then whatever is in memory is lost, but it has not made the system inconsistent. So the idea would be to keep on buffering each of these kinds of allocation decisions, keep on buffering them, and then once it has reached a certain size of the updates, then that particular log is actually flushed to disk. And now, in case there is a failure, you can go back to the log and see what has to be done to fix it. Okay. So there is some multiple levels at which this delay in terms of making the impact of a particular decision happen immediately. They try to cluster it, so it is getting clustered in memory first. If before you flush that particular log block onto disk, you lose it, you essentially lost whatever recent changes have taken place. Then once it has achieved a certain amount, then the whole log actually will go to disk, right? And then in case there is a problem, then you can use the log itself because it's persistent to fix it. Okay. And even here there are some interesting tricky things. It turns out when you are trying to flush the disk block, right? Your block could be multiple sectors. It's possible that it's multiple sectors, right? Now it may be that because of the way the sectors are laid out on the disk, it may be that the disk is closer to the end of the log than to the beginning of the log. Now if your elevator algorithm, let us say you are using that one, it goes ahead and flushes the end of the log first because it is closer to the head than the beginning of the log. Then what will happen if there is a crash? You will see some mangled thing on the disk and you will not know what to make of the thing, because basically the head of the log gives you all the information about how to read it. It tells you there are so many pieces I am putting together. It's something like when you have a document, you say page 1 of 12, page 2 of 12. Okay. So you know that if page 1 is missing, you know that it says page 2 of 12, you can figure out that some page 1 is missing. Or if you say page 11 of 12 and 12 is not there, you can figure out that page 12 is missing, right? So the front, essentially what happens is that the beginning of the log essentially tells you how to read the rest of the log, okay? And because it is a circular log, this information is important. Typically these logs are circular. So the only way you can read the log on a crash is by being able to figure out where the head of the log is, okay? Now if it so turns out that because of the disk elevator algorithm, it flushed the one side of the log first, the end side rather than the front side, then you can get into problems. So basically you have to, when you're flushing it, you have to ensure that you have to anchor the write of the log itself. What is anchoring? You first send the first sector of the log write that you have to do, the very first sector. So, one 512 byte actually has to go first. Of course, we are careful about, if you are really paranoid about data security, data being, not lost, you, even though you are writing something like 256 kilobyte of log, you first have to write the first sector to force that thing to the right place. The rest of it can go in any order, because the first sector has all the metadata about how to read the log in case of failure. Okay. So, all these things are done. Okay. So, that is why even simple things like allocating a free disk block, etc., can have a lot of ramifications in terms of when actually it makes it to disk. Okay. There is all kinds of things that are coming in the picture in between before it happens. Similarly, you can also have a free disk block. Okay. There are things relating to inodes also. So, again, a lot of abstractions are used, as I mentioned. You can get a locked inode which is using buffer read, because again inodes are kept in the disk and you are going to read it through buffer read. Okay. And then once you get that, basically somebody is doing a mapping between inode number and the block, and then you go to get the block and then read that portion of the inode. Similarly, if there is an IPut, that means this is iget, you get it from disk, IPut you want to push it to disk, and then you keep some reference counts, and if it turns out that reference count is 0, that means there are no users in memory, then you can write the dirty node. And this can be delayed also, or it can be, let us say, done immediately, okay, depending on the seriousness of the issue. Okay. One other important one is bmap, which basically given inode and byte offset returns the disk block number and the offset corresponding to it. And there are a few things like allocate, inode allocate and ifree. Again, all these things, just like block allocate, deallocate, they also have to go through some logging in case it is a logging based file system. Okay. So, name I is basically a slightly longer one. Given a path, get the locked inode. You have to parse each of the components of the name, and then you have to keep traversing the file system hierarchy. So, it's a fairly long operation. Okay. So, I think at this point I will stop. I will continue from here next class.